Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar Lecture Theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Friends, welcome to the second lecture on curved beams, which is lecture 18, where we are going to talk about curved beams with large initial curvature. In the last lecture, we discussed about the equation to determine stresses in curved beams with small initial curvature. Friends, welcome to this SwayamPrabha course offered by Department of Maritime Engineering at IIT Gandhinagar. The course title Maritime Structures with details on types, construction, pre-service analysis and design offered at IIT Gandhinagar. Welcome to lecture 18, beams, curved beams with large initial curvature. The fundamental difference between curved beams with large and small initial curvature is that the stress variation across the cross section of curved beams with large initial curvature is not linear. In the case of straight beams, it is true. For example, if you have a straight beam and if you have a curved beam with large initial curvature, if I try to draw the stress variation across the cross section of this, then you can say this is linear. Whereas, if I try to draw the stress variation across the cross section, it is non-linear. So, this is non-linear. So, interestingly friends, one should be able to compute the stresses at every depth, at every depth, at every depth, and this is a non-linear profile. So, I need to know this governing equation to compute the stresses at any point along its depth or height of the section. That is the fundamental difference we have between curved beams with large and small initial curvature. Further, experimental studies also show that for symmetric sections, the stress in the concave side is larger than the stress in the convex side. Now, the question comes, what is convex and concave side? Let us draw a curved beam in elevation. Let us draw the centroidal axis. Okay. For our understanding, let us mark the convex side and concave side. This surface is called the convex side and this surface is called the concave side. In simple thumb rule form, you must have seen a cave, okay? The cave. So, this is a cave. So, this resembles a cave, okay? So, this surface is concave and this surface is convex. Technically, we also call this as extrados, that is outer. Extrados means outside, and we also call this as intrados. Intrados means inside. Okay. So, the another name. So, concave side is also called as intrados and convex side is also called as extrados, and experimental studies show the stress on the concave side is larger, okay, compared to convex side. Let me draw this schematically and explain. Let us say I draw curved beam profile. Let me draw this line where the neutral axis or the stress is 0. Let me project these points at any section I want. So, this is the section where I want, and we know this is going to be the convex side and this is going to be the concave side, and experiments show that this stress is higher. Therefore, I will have higher stresses on the intrados and smaller stresses on the extrados, and the variation is non-linear. Okay. So, these stresses So, these stresses are large in intensity. This value is higher compared to this value. Okay, this is small. And this variation is non-linear. Experimentals show this. Okay, so we have to, this is the stress distribution across the cross section of curved beam with large initial curvature. Let us now start deriving this equation. So, we can now write a very important statement. Since these stresses are not equal, okay, I can now say neutral axis does not pass through the centroidal axis. Okay, that is a very important observation here. Centroidal axis, the geometric center. The section may be symmetric. Centroidal axis can be at the center of the depth of the section, but the neutral axis where the stress is 0 does not pass through the centroidal axis. Can you tell me why? In simple terms, friends, the stress distribution in the extradas and intradas are not same and the variation is nonlinear. Therefore, the neutral axis will not coincide with the centroidal axis. Okay? Therefore, there is going to be a shift of the neutral axis from the centroidal axis, which is now going to govern this equation of getting the stresses. Okay? So, now let us now consider a curved beam with radius r. Obviously, the radius r is always referred to the geometric center, okay? Whether it is curved beam with small or large initial curvature does not matter. The radius of curvature or the radius of curvature of the curved beam always refers to the centroidal axis or the geometric center. So, r is the radius of curvature. Now, let us say this curved beam, it is subjected to a moment here. Okay. Most importantly, this moment tends to close the curvature. We can also write in simple terms, this tends to decrease the curvature. So, if you have a moment applied in this form, this is taken as positive. Generally, in bending theory, we say sagging moments positive, hogging moments negative. So, here we do not say that way. We say that when the moment tends to close the curvature, then it is taken as positive. When the moment opens the curvature, okay, then it is negative, and so on. Okay. Therefore, when I have a flat beam, let us say I have a flat beam, okay, I make a moment and make it curve. I am applying a moment. So, when the moment is closing the curvature, decreasing the curvature, one can easily estimate that extradas, okay, will be in tension, is it not? When you try to elongate the fiber, all these fiber will get elongated, is it not? All these fiber will get contracted. So, I can say intradas is in compression. So, I can go back to this figure and mark this as compressive stress and this as tensile stress. Can you do that? because this segment is extradas, this segment is intradas. Okay. So, this is what we learnt, which is different from that of a conventional beam, where the moment is assigned to be a specific designated value in terms of sign convention, provided you fulfill this condition. Okay. Now, let us take a member. Let us consider, I am drawing a figure, you also please draw this parallelly on your paper. Let us do it carefully, because this figure is very important for us. So, let us mark the extradas fiber, let us mark the vertical line, which is going to indicate the center of curvature O. Okay. Now, let us mark the intradas. Okay. Let us now mark the radius of curvature. Let us draw a line. We call this line as a centroidal axis. Okay. And let us say this axis is at a distance r from the center, that is the radius of curvature. Okay. Now, let us draw a neutral plane, because you know neutral axis and centroidal axis do not coincide, because the stress distribution across the cross section is non-linear. So, now let us mark another layer. I am using different color, possibly you are able to see them. At a distance E measured towards the center of curvature. Okay. So, E is measured towards the center of curvature, okay, measured towards here. So, I call this layer as the neutral layer. One may ask me a question, why neutral layer will shift towards the center, why not away from the center? Good question. Let us see this stress distribution. The stress distribution is larger at the bottom and smaller at the top. The neutral axis therefore will shift towards this point, is it not, from the center. So, neutral axis is shifting towards the center, and that shift is called E in my figure. Okay. Now, let us take two segments. Let us take two segments. Okay. Let us mark these segments as A, B, points on extradas and intradas, and this is C and this point is D. Okay. So, AC is a segment on extradas, BD is a segment on intradas, which makes an angle, okay, D phi at the center. Okay. Now, let us take another layer. Let us draw a thick layer for our understanding. Let us take another layer PQ. Okay, we have taken PQ layer. Now, if I designate a layer, it should be measured, and I measure this layer from the centroidal axis. Friends, very important, the distance of any fiber where you want to measure the stress is always measured from the centroidal axis, whereas in conventional beam theory, if you look at M by I, stress by Y, E by R, Y is the distance of any fiber from the neutral axis. Okay. Incidentally, in a flat beam, neutral axis and centroidal axis may coincide. that is a different story. But we measure the distance of the fiber from the neutral axis, whereas here we measure the distance of the fiber from the centroidal axis. Let me rub this. Okay, so that is the difference we have here. Of course, if you want to know the distance of that fiber from the neutral axis, you have to add simply E to it. For example, if you want to know the distance of the fiber PQ from the neutral axis, then it should be Y plus E, right? Is it not? So, I have to add E to this. Okay. So, this for our clarity. So, please remember it is a very important change in the conventional derivation. Okay. Now, I apply a moment which is of a specific order, which is closing or decreasing the curvature. So, I call this moment as positive. Okay. The moment is not positive or negative because it is sagging or hogging, etc. That is in a different theory. Here, moment convention depends on whether it closes the curvature or opens the curvature. Okay. Now, I have marked a moment in such a order that the curvature will get decreased or close. Okay. So, this is a fundamental figure we have with me now. So, let us for our clarity also mark this surface BD as concave side, also called as introdas, this surface AC as convex side, also called as extrodas. Okay. It is a basic figure. So, figure 1, basic figure of nomenclature. I stay few seconds here, just look at the figure, draw carefully, once again check the notations correctly, then mark and understand them clearly. It is very important. Okay. Now, I will move forward. Let us consider element A, B, D, C, which subtends angle d phi at the center. Okay. I have considered segment ABCD which subtends an angle d phi at the center. Correct? I have done that here. When moment is applied, this will now differ, or this segment deflects or changes to A, B, C dash, D dash. Let us mark the C dash, D dash. So, I am just drawing an enlarged view of ABCD alone. I am just taking ABCD alone, drawing an enlarged view here for our understanding. Let me do that. So, let me draw the center line. Let me draw AB. Let me draw BC. Let us say this is A, this is B, and this is C, this is D, cutting D phi at the center. Okay. Now, I am drawing the extension. When I apply M, AC will get extended and C will become, let us say, C prime, and BD will get contracted and D will become D prime. Let us keep AB as it is. So, we will not rotate AB, we will only rotate the point C and D. So, C prime and D prime. Okay. Let me join this. Can I do that? Let us rub this and write it here. It's better. Write it here. D prime. So now this is my shift. Now the point. Okay. So now let me mark the central and neutral axis also. So same color. So central was red color. I will mark red color. This is centroidal axis, and neutral axis was in purple color. I will mark purple color. This is neutral axis, and the distance between these two we know it is E marked here. Let us now mark the layer PQ also in blue color. Layer PQ in blue color. Now what happens? Q has shifted to Q dash, correct? I will just enlarge this figure. This is Q, I love this. This is Q shifted to Q dash. Okay. Let us call this angle subtended by the new shift as d phi prime. Okay, small angle of shift. Now it is applied to M, I am marking M. Okay, I am just reducing the figure. Please draw this figure carefully, friends, and try to understand the nomenclature. So now I can write that we have observed that neutral axis shifts towards the center of curvature for the applied M. When you apply M like this, neutral axis will shift towards the center, okay, towards the center. Okay. Now, let us draw the cross section of this. Let me draw the figure again of the curved beam. So, let me project the points. I can draw this cross section anywhere I want along extradas and intradas. I have taken at this point, rigid point, okay, peak points. So, let me draw this cross section. Let me draw a vertical line. Then let the cross section be of any irregular shape. We will not bother about the shape for the time being. Any irregular shape. Okay. So, let us mark the centroidal axis. We call this as CG. Let us mark the neutral axis. Okay. We call this axis as NN. NN stands for neutral axis. And this axis as XX. XX stands for centroidal axis. Okay. And we know that this shift is indicated as E, and we know that this from the center of curvature is R, is it not? Radius of curvature is always marked to the centroidal axis, geometric center. Okay. We call this tip as R intradas. We call this external tip as R extradas. This is center of curvature. Okay. From the centroid, we call this as H intradas, and we call this as H extradas. Please note, friends, H is measured from the centroidal axis. R is measured from the center of curvature, capital R is measured to the neutral axis, to the centroidal axis, and neutral axis is shifted towards the center for the moment applied like this. Okay? Nomenclature. Having said this, so we said that we will not rotate AB, we will only rotate CD to C dash D dash. Okay? Now, let AB surface is assumed to be fixed, not rotating. Only CD plane rotates. Okay? To C dash D dash. See here, AB is not rotating, CD is rotating to C dash D dash. Okay? And that subtends an angle d phi dash. Okay? This angle is d phi dash. This angle is d phi dash. Okay? So, initial length of the fiber PQ, which is measured at a distance y from the centroidal axis, is given as, see here, I am measuring the fiber PQ from the centroidal axis, this is central axis y. Okay? I want to know this length. Can you compute this length? It is very easy. Is it going to be r plus y of d phi? Because this distance is r plus y and this is d phi. I want to know this length. It is very simple. Length of the r is nothing but r theta. So, I can now write it here, is given by r plus y of d phi. Can I say this? Equation 1. Now, when I apply moment, when the moment is applied, this fiber length changes. Is it not? So, from PQ, it has become PQ dash. So, now I want to know the change in length of the fiber. Due to applied moment. I will open this figure. Can you give me a hint how I can do it? You know, this is given as d phi instead of d phi prime, friends, we will take this as delta d phi, okay, for our understanding. Delta d phi. Please make a change. So, we will say this is extending an angle subtending delta d phi prime. Okay, we will write it here. We will rub this subtending delta d phi, small angle of d phi. Now, I want to know the change in length of this fiber. I look at this figure, I will help me to do this. I want to know this actually, right? I want to know this. Think about it, what would be this value? Because you know this is neutral axis and this is E and this is Y. Can you say this is going to be equal to is going to be equal to y plus E of del d phi. See this figure? This is E, this is y. So, this becomes y plus E, this is d phi. So, can I say r theta, that is y plus E d phi? So, I have said that, okay, y plus E d phi. Then what is E in this case and what is Y in this case? Y is the distance of the fiber PQ from the neutral axis, from the centroidal axis, whereas E is the shift of the neutral axis from the central axis towards the center. Let us be very clear about this. Let me also write it clear. This is E. Okay. Now, I can this is equation number 2. So, this change in length. So, if you want to find the strain, so the strain epsilon caused by m is given by change in length by original length. So, epsilon is now going to be y plus E of del d phi by r plus y of d phi. Can I say that? Because original length is r plus y, change in length is y plus E. So, I have used it here. Okay, equation number 3. Now, I want to find the stress. Okay, the stress or the corresponding stress is given by Young's modulus times of strain. So, which I can now say stress is going to be E into del d phi by d phi y plus E by r plus y. Can I say that? This is equation number 4. When I write this, I make an assumption, assuming that the longitudinal fibers do not deform, okay, because del d phi is very small in magnitude. Okay, I computed the stress now. Let me try to plot this variation for different values of E and Y. So, if I have a curvature, if I try to plot the stress variation, okay, this is the centroidal axis and this is the neutral axis, this is NN, this is XX and the fiber is PQ and this is Y and this is E. Let me plot all these points first. Let me project all these points. I am now trying to draw the stress variation. So, the stress is going to be smaller here and very large here. So, at this point, which is the neutral layer, stress is 0. Okay. So, the stress distribution is non-linear. E has shifted towards the center of curvature. Okay. There is a shift here towards the center of curvature, right, and moment is applied like closing the curvature. That is very important for sign convention, friends. Okay. Now, on the basis of assuming that every cross section normal to the centroidal axis remains plane and perpendicular before and after application of M. Then assumption we make, okay? We make an assumption, one of the basic assumption. On the basis of this assumption, okay, we can then write total compressive force is equal to total tensile force if this assumption is true. Now, since the average stress in the concave side is higher, is it not? See here, the average stress on the concave side is higher than the convex side. Neutral axis shifts towards the center of curvature. Okay. Therefore, friends, equating the sum of internal forces to 0, we get integrating the sum of internal forces over the entire area as 0, we get the following. We already have an equation for stress. Let us do that. So, stress is going to be E times of d phi by d phi y plus E by r plus y of dA equal to 0. Okay? So, which is equal to E del d phi by d phi integral A y plus E by y plus r dA is 0. Equation number 6. Now, in this equation we can see this term cannot be 0. Okay? Essentially E and del phi is a physical quantity. This cannot be 0. Then what can we say? We can then say that since E del d phi and d phi cannot be 0, we can simply say integral y plus E by y plus r of dA should be set to 0. That is the only option we have, is it not? So, I can expand this. Expanding, we can say over area A y by y plus r of dA plus E times of 1 by r plus y of dA is 0. Can I say that? I have just expanded equation 7, calling this equation number 7a. It is one and the same. Okay, let us rewrite this equation 7a again. I am writing equation 7a again. Y by r plus y of dA over A plus E times of over A 1 by r plus y dA is 0. Okay? Let us look at the first equation of this. The integral y by r plus y dA over A is some factor of A. Where? m. Remember friends, capital M is the moment, small m is a factor. So, use them very carefully. Okay, use them very carefully. So, where small m is a constant depending on the cross section. Okay, the quantity MA, the quantity MA is called modified area of the cross section. Okay. Now, let us look at the second integral. The second integral, I will pick up that. Then the second integral, which is picked up here, e times of 1 by r plus y dA can be simply solved with some modification. I write e r plus y minus y by r plus y minus y, or let us say, write it the other way. We say r plus y minus y by r. Okay, into 1 by r plus y dA. Can you say that? Because you know this term will be actually 1, is it not? This term is 1 because this gets cancelled, this is 1. Okay, so I am rewriting this same, not making any change. If I agree, then it is going to be equal to now e by r integral r plus y by r plus y dA. See, I am using r plus y by r plus y dA. Okay, that is the first term I have written, minus, there is a minus sign here, okay, minus integral y dA by r plus y of area. Can I say this? Okay, having understood this, we can now say this is going to be A. So, I can now say it is E A by R minus. Friends, can you tell me what is this value? Turn back your notes. We already assumed that this integral is called MA. So, this integral is called MA. So, can I say this as minus MA of E by R? Okay. So, now equation 7a can be written as, what is equation 7a? Equation 7a is the integral. This is equation 7. Is it not? Because this we already said is MA, this we just computed. I am adding and saying equation 7a can be written as, is going to be equal to MA plus E by R of A minus E by R of MA. Can I say that? And what is this equal to? What is the RHS of equation 7a? This is 0, right? So, let me equate to 0, friends. So, then I can now simplify m plus E by R minus E by R of m is 0. Okay, A goes away, which I am now saying m is equal to E times of small m by R minus 1 by r. Is it not? So then I can say this is equal to E by r times of m minus 1, that is my m. Okay. So if you want to write E, because E is the location of neutral axis, I can then write, I am rewriting it again, E m is equal to E by r of m minus 1. Therefore, E is going to be m by m minus 1 times of r. So friends, if I know m for a given cross section, if I know the radius of curvature of the curved beam, I can locate the neutral axis from the centroidal axis. Okay? Friends, to locate a neutral axis in conventional beam, we need to know the stress values. But to locate the neutral axis in curved beam, we need to know only the geometry. So, the neutral axis location does not depend on the stress values. It depends on the geometry. How can I say that? Let me write the statement first. The neutral axis location is geometric dependent because M is called modified area, which is dependent on cross section, shape and size, and R is the radius of curvature of the curved beam. So, here no stress coming into play. So, neutral axis can be located if you simply know the geometry. It is very interesting observation, friends, very interesting. I call the equation number 8 if my sequence is correct. Okay. So, let us write that equation. It is important to note that in the cross section, applied moment should be equal to the resisting moment. Is it not? For the system to remain in equilibrium. If that is the case, this equation is valid. Equation 9 is related to other form of m. I am writing it here. If you know this value, you can also get m as minus E by r minus E. I leave this derivation to you. You can try this. This is equation 9 actually. Okay. So, equation 10 is here. Now, I know the value of stress. Let me substitute the value of stress, and that is going to be equal to E times of del d phi by d phi integral y plus E y plus r dA into y is m. Equation 11. Okay. So, we will extend this equation and try to find the stress distribution across the cross section in the next lecture. So, friends, in summary, we learnt that how curved beam with large initial curvature behave like the stress distribution is nonlinear. I can locate the neutral axis which is shifting towards the center of curvature by an amount E from the centroidal axis, and it can be located only based on the geometric shape and size. So, when you have a neutral axis where the stress is 0 is dependent on only the geometric shape, can I say curved beams are form dominant? Okay, that is very important observation we make here. We stop here. So, please attend the next lecture as well to complete the derivation and to get the stresses across cross section distribution, and then we will work out on different factors of getting m, the geometric modified parameter m for different standard cross sections where curved beams are used. Then we will do some numerical examples of crane hooks to find out the stresses in a curved beam. Thank you very much. Namaste.